Okay, so in this question, this lift is descending with uniform acceleration. It descends from rest for 8 seconds until it reaches a speed of v. Okay, tension in the lift cable is 50,400 newtons. So show the magnitude of acceleration of the lift is 0.8. So what we do is, of course, we use Newton's second law, okay, in the direction of motion. Okay, so it's accelerating downwards. So we've got 5,600 g. Now that's the weight I've got here of the lift, the mass times gravity value. Take away the tension in the string, in the cable rather, which is 50,400, and that will equal the mass, which is 5,600 times the acceleration. So then we plug in the 9.8, take away 50,400, 5,600A. We get then 4,480, which equals 5,600 A, and then to get A, of course, then you divide, don't you? Take that 5,600 over, divide to get your A, which I'm assuming then will be our answer, indeed, 0.8 meters per second squared. So part B then, it says find the value of V. So now we turn this then into equations of motion, right? Because we know we start from rest, okay? So U is 0, the initial velocity. We know this, it takes a time of 8 seconds until we get to this speed of v, yeah? Okay, and we know the acceleration now is 0.8. So to get v, we simply use the equation of motion. We know u, we know t, we know a, so I'm simply going to use v equals u plus at, okay? So v then is my capital V, the speed, and that will be u, which is 0, plus then a, which is 0.8, times the time, which is 8. So V then will be that, and you end up having 6.4 when you times them meters per second. Okay, so then it says in the question that the lift maintains this constant speed of V for 25 seconds before decelerating uniformly to rest. Total time for the descent is 40 seconds. Okay, so it says draw a sketch of the velocity time graph of the motion. So we need to draw a velocity time graph here. So remember the velocity time graph, we have label the axes, okay? Remember velocity here, and make sure you put the units in, meters per second, and then we do time along here, okay? Time here, which is in seconds, okay? Now it started from rest, if you remember, okay? And for 8 seconds in part A now, if you remember, it started from rest 0, and for 8 seconds it accelerated until it reached a speed of 6.4. Okay, so we can put on here our time of 8 seconds, and that will be 6.4. Now it says it maintains the speed, doesn't it? The lift maintains this constant speed for 25 seconds. So 25 seconds along, okay, it's going a flat line, yeah? Gradient is 0, because remember the gradient tells us the acceleration, and it stays at that speed 6.4 for a total of 25 seconds. So if we add 25 onto that, you get 33, and then it uniformly decelerates then to rest, okay? So and it says the total time for the descent is 40 seconds. So we can see then that we've got 40 seconds there. We've got 7 seconds where it's decelerating. Yeah. So I've got there my completed velocity time graph. It says then calculate the total distance the lift descends. And remember with velocity time graphs, you can get the total distance. Okay. So total distance equals the area under the graph. Okay, so the area then is the trapezium, yeah, formula. So half A, this side here, which is 40, plus then the side that's parallel to it, which is 25, times then the gap between them, which is 6.4. So that straight away will give us the distance. So we get 208 meters. Okay. E then says find the maximum tension in the lift cable during the motion. Now, if you think about it, right, there's 3 stages of motion, isn't there? There's the acceleration phase, there's the constant speed sort of phase, and then there's the deceleration phase. Now, what I would do, just to be careful here, is just to check each particular phase, right? And for that, we need to know the acceleration there, of course, was 0.8. We worked that out. To get the acceleration here, we need to work out the gradient of this, yeah? And because we don't know what the acceleration is when it's slowing down, or what the deceleration is rather. But remember, you can get the deceleration, okay, simply by looking at the change in velocity. Okay, so it's going from 6.4 to 0. Okay, so that'll be a negative change of 6.4. Okay, divide by then the time. Okay, which is 7. So I'm doing a little triangle really to work out the gradient. Okay, so minus 6.4 is that there, the fall, and the horizontal distance is 7. Now, I don't know if that simplifies nicely on the calculator. Actually, it just gives us minus 32 over 35. It sort of gives us whole numbers there, so maybe we'll go with that. So what you do need to do then is look at the tension in each phase, right? Okay, so if you remember the lift now, I'll draw a quick sketch here, right? So you've got the tension in the cable, you've got the weight, okay, which is 5,600 G. Okay, now in this phase here, I don't need to actually work out the tension, if you remember. Okay, so in the first stage, I don't need to work out the tension because the tension was given to us, wasn't it? That was part of the question setup. So it said the tension was equal to 50,400 newtons, yeah? Then in the second stage, okay, where the acceleration is 0, if you think about it, if the acceleration is 0, then the upward force will equal the downward force, okay? Because ultimately, you've got the resultant force equals to mass times 0 acceleration, yeah? Which means T is equal to 5,600 G, okay? So that would be, on my calculator, 5,600 times 9.8, and we get out 54,880 newtons. Okay, so the tension then is greater, okay, in the second stage, and you'd expect that, wouldn't you? Because it's going at a constant speed. It's no longer accelerating downwards. Okay, so slow down a bit. Let's look at the third stage, where it's actually decelerating. If we use Newton's second law again, okay, we'd have 5,600 G, okay, which is the downward, because it's going down. I should have done that there, really, shouldn't I? I should have done 5,600 take away T. It doesn't matter, because you still get that. But in the third stage, you've got 5,600 G, take away the T, and that will equal the mass, which is 5,600, times then the acceleration, which we've got up there to be minus 32 over 35. Okay, so then when we work this out, we get tension equal to 5,600 times 9.8, and then take that over, so you get plus then 5,600 times that fraction. Now I'm thinking this is going to be greater. This is going to be where I said it's most, because it's decelerating, which means the cable's got to do more work. Okay, so when I type that into my calculator, indeed, I get 60,000 newtons. Okay, so max tension occurs when decelerating, because of course the cable is doing its most work to slow it down.